Trillion-parameter AI training runs are no longer simple programming tasks. They are rigorous, high-stakes exercises in massive computational physics. This chart shows the SWE Bench verified evaluation for coding agents. Kimi K2 Instruct scores 65.8, outperforming both Claude 4 Opus and GPT-4. Looking to the right at the Live Code Bench evaluation for competitive programming, we see a similar gap where K2 scores 53.7. These outputs come from a 1.04 trillion parameter mixture of experts model, pre-trained on 15.5 trillion tokens with absolutely zero loss spikes. Reaching these metrics exposes a strict physical limit in model development, the exhaustion of high-quality human data. Simply brute forcing scale yields rapidly diminishing returns. Surpassing closed-source benchmarks requires engineering extreme token efficiency across the data, optimization, and architectural layers. When pre-training data is limited, repeating high-quality knowledge and mathematical datasets across multiple epochs causes severe model overfitting. K2 multiplies tokens through chunk-wise autoregressive rephrasing. To process long documents, the system slices source material into blocks, routing them to a rewrite model. This alters each section's syntax without degrading accuracy. Finally, the system stitches the chunks sequentially back together. This produces a synthetic dataset that provides a fresh learning signal on each pass, avoiding the rigid memorization triggered by raw text repetition. On the simple QA benchmark, training on one epoch of rephrased data yields higher accuracy than training on 10 full epochs of the original raw text. Data preparation at this scale operates as the synthetic multiplication of token utility before the training run begins. To maximize the learning extracted from that data, K2 moves away from the industry-standard Atom-Abelewit optimizer. The model trains using the Muon optimizer. Muon uses a Newton-Schultz iteration, which provides superior token efficiency under a fixed compute budget. This dual line graph tracks maximum attention logits over time. Scaling Muon introduces severe training instability. Maximum logits explode past a magnitude of 1,000, causing loss spikes. Standard logit soft capping fails because dot products grow excessively before the cap applies. Similarly, query key normalization fails on K2's multi-head latent attention architecture because the key matrices are never fully materialized during inference. To stabilize the run, the engineers built MuonClip, a custom optimizer integrating a mechanism called QK-Clip. This diagram maps latent attention components. QK-Clip locally monitors each attention head, intervening when one exceeds a threshold of 100. It dynamically rescales the unshared query and key weights to bound logic growth. Shared rotary keys are deliberately excluded to prevent interference. Returning to our dual graph, we can see the localized control in action. The maximum logits hit a hard ceiling at 100 and eventually decay into a stable operating range. By deploying MuonClip, the K2 base model processed 15.5 trillion tokens on a 1 trillion parameter architecture without a single training crash. By eliminating logit explosion mathematically, the architecture enables the Muon optimizer to maintain its high token efficiency even at this trillion parameter scale. K2 is built on a 1.04 trillion parameter mixture of experts architecture. Despite its size, the model operates under severe sparsity, activating only 32 billion parameters per forward pass. This chart models the sparsity scaling law for Muon-trained MOE models. By fixing the activated expert count at 8, you can consistently lower validation loss simply by adding more inactive experts to the total architectural pool. Following this law, K2 operates as an ultra-sparse architecture, activating exactly 8 experts out of a total pool of 384. However, while the expert count scales up, the attention head count scales down. K2 utilizes 64 attention heads, half the amount found in DeepSeek v3. Processing a 128K sequence length with 128 attention heads inflates inference flops by 83%. K2's design accepts a roughly 1% increase in validation loss to eliminate that massive inference overhead. This architectural compromise is mandatory for agentic intelligence, which requires rapid, continuous processing of long contexts that high-head models make economically impossible. A pre-trained base model holds vast mathematical and linguistic priors, but it lacks the capacity for multi-step reasoning, long-term planning, and direct environment interaction. To teach tool use, K2 relies on a synthetic data pipeline. First, it generates a repository of tool specifications. Second, it generates distinct autonomous agents and tasks requiring those tools. Finally, it rolls out millions of synthetic trajectories where agents execute the tasks. These trajectories are aligned using reinforcement learning with verifiable rewards, or RLVR. Instead of relying on static human labels, the model learns through self-critique. It tests its own outputs against verifiable ground truths, such as a successfully compiled code block or a completed API call. RLVR forces the model past basic imitation and into open-ended, autonomous problem-solving, establishing its high scores on coding and engineering benchmarks. Kimi K2's performance shifts away from a reliance on raw compute scale. It is the product of an interconnected stack. Chunked rephrasing amplifies the learning signal. The MuonClip optimizer guarantees mathematical stability across the 15.5 trillion token run. Ultra-sparse MOE architecture ensures complex inference remains economically viable. And verifiable reinforcement learning bridges the gap to autonomous action. Kimi K2 proves the next era of foundation models depends on engineering efficiency into every layer of the stack.